Yes, so today we have Augusto, who is a researcher at Inductive Research Labs. His main line of research is centered around machine learning for fundamental mathematics. Specifically, he's focusing on the application of machine learning for solving combinatorial optimization problems. And today he will present us his most recent work on the scope of geometric deep learning, which, as you know, is a very hot topic in deep learning today. And he will talk us specifically about the equivariant neural networks for recovery of Hadamard matrices. So thank you again, Augusto, for your availability. And when you're ready, please, you can start.
Thank you for having me. Thank you for the opportunity of sharing a little bit of my work at Inductive Research Labs. I'm just trying to find out how to share a single window instead of my entire desktop. At least I don't think I'm finding here the window that I need to share.
If you share the entire desktop and then you put the presentation in full screen, then it shouldn't be a problem as well. But yeah, take your time. Don't worry.
Yeah, so I don't know if everyone can see my slides.
Yes. Okay. Can you make it full screen?
Well, I think this is what Google Slides does when it's in full screen. At least I've already entered presenter view. So I think I can stop screen sharing and share just a portion of the screen though. Let me try that. So
it's a bit cropped right now, at least.
Yeah, this has a sidebar that allows me to expand, I think.
Okay.
Yeah, I don't think this portion of the screen works very well. Okay, so I think maybe like this, it's a little bit better. Okay, so I think that's now the entire slides are shown, right?
Yes.
Or is it still a little bit weirdly cropped? Okay, so I think we are good to go, right?
Yes, Augusto, please.
Okay, thank you. So in this presentation, I'm going to talk about equivariant neural networks for the recovery of Hadamard matrices. So a brief presentation outline. First, I'm going to talk a little bit about why we want to use machine learning for combinatorial optimization. Then I'm going to introduce Hadamard matrices. I'm going to explain what they are, some properties, and talk a little bit about Hadamard's conjecture. Then I'm going to explain why we want to use machine learning for the Hadamard problem. And then I'm going to talk a little bit about problem symmetries and how we can exploit them, and give, because this is the main focus of geometric deep learning, I'm going to give a quick introduction to geometric deep learning, just a key concepts so people can understand better the presentation. And then I'm going to show how we can, using these concepts of geometric deep learning, design a model that is equivariant to permutations. And then we're going to see the few results that we had using our models. Okay, so what is combinatorial optimization? So basically, combinatorial optimization problems deal with finding optimal objects, that is, objects that minimize or maximize some objective function from a set of finite objects. For example, the traveling salesman problem, the max cut problem, and the big packing problem are all combinatorial optimization problems. And for example, a traveling salesman problem even is a problem that basically we are given a list of cities and the distance between each city, and the goal is to find a path that visits all cities at least once and has minimal distance. So here in this case, the set of possible objects is the set of all paths that visit each city at least once, and the optimal object will be the path that has minimum distance. So why machine learning for combinatorial optimization? Well, firstly, efficiently solving combinatorial optimization problems requires the development of heuristics, and usually these heuristics take quite a long time to find. For example, the traveling salesman problem that we saw in the previous slide was first formulated in the 30s, and only in the 70s could we solve instances with more than 2,000 nodes. And then in the 90s, more progress was made and we could solve instances with 80,000 nodes. And at the moment, the problem is largely considered solved, since we can, solve instances with millions of nodes with very, very small margins of error. However, these heuristics were the result of intense research by several specialists in several different fields of mathematics and computer science, and they are non-generalizable to other problems. So if now we want to solve the scheduling problem or the bin packing problem, we need to find new heuristics unless we try to make some sort of reduction of one of these problems to the traveling salesman problem. So ideally, we would like to have some sort of framework that generalizes well from problem to problem with very little effort. And this replacement of human design heuristics has already happened with chess and Go. For example, before AlphaGo, different heuristics had to be developed for each different game. Now we simply have an algorithm that learns through self-play, and if we want to design another AI for a completely different game, we just need to train the model again, but it's always the same algorithm. So ideally, we'd like to have some sort of framework like this for combinatorial optimization and machine learning. Also, we are entering a regime where we have tons of data, because some combinatorial optimization problems are solved on the daily basis. For example, the scheduling problem is solved daily whenever we want to schedule trains or flights or any other type of application that you can think of that would benefit from some type of schedule. So we are entering a regime where we already have a problem instance and their respective solutions. And there are already quite a few works focusing on machine learning for combinatorial optimization. For example, in this first paper, the authors use reinforcement learning to tackle the max-dat problem in graphs and actually achieve state-of-the-art performance after training. And in the second paper, the authors will use, again, reinforcement learning to learn better branching decisions in variable assignment in SAT solvers. So now we are going to talk a little bit about Hadamard matrices. And Hadamard matrices are very simple objects. They are simply squared matrices whose entries can only attain values of either -1 and 1, and whose rows are pairwise orthogonal. And by pairwise orthogonal, I mean that the dot product of every two distinct rows is 0. For example, here we have a Hadamard matrix of size 4. And you can easily see that if we take the first row of the matrix and we dot product it with every other row in the matrix, the result would be 0. So a few quick properties of Hadamard matrices. And Hadamard matrices of all the square matrices whose entries can be only either -1 or 1 have maximum determinant. And the reverse implication is also true, meaning that if a binary matrix, and here I'll use binary matrix to refer to matrices with entries in -1 and 1 and not entries between 0 and 1. So any binary matrix with determinant that attains the bound on the screen is necessarily Hadamard matrices. So small question, can we have Hadamard matrices of any size? And the answer is no. Hadamard matrices must be of size either 1, 2, or a multiple of 4. And then slightly bigger question is, for all multiples of 4, is there a Hadamard matrix of that size? And the answer is, we don't know. In fact, this is still a conjecture, and at the moment is believed true, and it's conjectured that for any number that is a multiple of 4, there is in fact a Hadamard matrix of that size, and this is known as the Hadamard conjecture, or Hadamard conjecture, Hadamard's conjecture. And at the moment, the smallest order for which no Hadamard matrix is known is 668, and the smallest order for which no symmetric Hadamard matrix is known is 236. And for most orders, only a few equivalent classes of Hadamard matrices are known. And I'm going to explain now what an equivalence class is. So basically, two Hadamard matrices are said to be equivalent if one can be obtained from the other by permuting or negating rows. And by negating rows or columns, I simply mean that we take every element in that row or that column and we multiply it by -1, as it is illustrated in this picture here. So basically, these two matrices are said to be equivalent because h of n was obtained from h by simply negating one column, and all the matrices that we can see here on the right are all said to be equivalent because they all result from one another by introducing permutations to rows and permutations to columns. So a few curiosities about equivalent sizes, and the first one is that the first size for which more than one equivalent class of Hadamard matrices exists is size 16, and we can see that the number of equivalent classes seems to grow very rapidly. Of course, we don't know if this is the case because, of course, knowing the distribution of the number of equivalent classes for all orders is an even harder problem than solving the conjecture. But we can see that for size 32, already more than 13 million matrices exist. Also, the last size for which all matrices are known is 32. So for even very small orders, we already don't even know if there are all the equivalent classes that exist, or even if there are, or even if there are any more equivalent classes to discover. So the search for Hadamard matrices, and the moment the search for Hadamard matrices has been, most Hadamard matrices have mainly been discovered through constructive methods, meaning that, what is a constructive method? Basically, a scientist, usually a mathematician, imagines construction, and then it proves that that construction is a Hadamard. For example, we have a few famous constructions such as Pauli's construction, Williamson's construction, and Sylvester's construction, which I'm going to explain now because it is rather compact, and it works as follows. Basically, if we look at the rightmost matrix, we have the full construction, and the matrices are constructed by simply noticing that if we stack from a Hadamard matrix, we stack them in blocks, with the first 3 blocks being the initial matrix and the 4th block being the negation of the matrix, we now have a new Hadamard matrix. Using Sylvester's construction, we can obtain matrices for any order that is a power of 2. However, most of these constructive methods, though very, very clever, they leave gaps in the orders for which there are no matrices. For example, Sylvester's construction yields matrices of orders 2, 4, 8, and 16, but misses n equals 12. So using Sylvester's construction, we cannot obtain a Hadamard matrix of size 12. So this motivates a more general approach, because if now I want to find a matrix of size 12, which it's just an example because it already exists and there's only one I would need to find a new construction and prove that that construction in fact yields a Hadamard matrix. So people have tried to find matrices with computers. For example, Jeffrey Klein, and this paper will be repeated throughout this presentation, uses a search and recovery algorithm to find matrices of up to size 228 and a symmetric matrix of size 116. And this matrix of 116 is actually important because at the moment such matrices had only very recently been discovered through very optimized search procedures. And then there are also other approaches. In one of them, they use genetic algorithms for constructing Hadamard matrices, and the genetic algorithm yields matrices of size 52 through to 64. And of course, that 62 is a very small order when compared to size 668, which is the last known Hadamard matrix. But please consider that there exists approximately 9.6 times 10 to the 813th power of binary matrices of size 52. And there are only 10 to the 82nd power of atoms in the observable universe. So the state space is very large. So why machine learning for the search of Hadamard matrices? Well, first, this is motivated by the success of its applications to other problems. For example, the ones we've seen before, where authors use machine learning and achieve state-of-the-art performance in the max cut problem. Then it is a hard combinatorial optimization problem, but its formalization is very simple. So it's very simple to explain what we are trying to do. But the problem is hard to solve. And there are also a huge number of possible approaches that one can think of. Can use just machine learning as the authors of the previous paper for the max cut problem, or we can use machine learning for better variable selection in constraint satisfaction programming, or we can try to improve local search methods. Also, this problem allows us to explore ways to exploit domain symmetries, and this will be the main focus of this presentation. It will be mainly about exploiting domain symmetries in the input data. Also, we can develop, hopefully, by studying hard combinatorial optimization problems, we can develop techniques that can generalize well to other instances. However, right now, there is no previous work to the extent of our knowledge that tries to tackle the search for Hadamard matrices using machine learning. Moreover, as a consequence, there is very little information on what types of deep learning models would work well with this type of binary data as input. Therefore, before trying to simply start using machine learning to immediately find Hadamard matrices, we set ourselves a simpler task, but that already appeared in scientific literature, which is Hadamard matrix recovery. And Hadamard matrix recovery is in fact a key component of the algorithm for finding Hadamard matrices that was of the paper mentioned before by Klein that found matrices of size 228. So what is the recovery task? The recovery task is simple. We start with a Hadamard matrix. We hide, and by hide, I mean we set to 0 a few entries, and then we train a neural network to predict the missing values. So it's something like this. We have a Hadamard matrix. We select a few entries. We set them to 0, and then we train a neural network to predict the missing values. So we need to predict the values that should replace the zeros in their respective positions to obtain a Hadamard matrix. And this is what we refer to as the recovery task. Okay, in our work, we've used two experimental setups. The first setup and the simpler one is we train and we test in the same equivalence class. So we have a representative of an equivalence class, and then from that representative we generate the training and the validation data. And then we have a harder experimental setup where we train our model and we test in using for validation and for training the joint equivalent classes. So all the training data comes from a few equivalent classes, and all the validation data comes from another equivalent classes. Why is this hard? So even the simpler setup, we need to recall that the definition of equivalent class. So completing or reconstruction of single equivalent class is not the same as learning to memorizing a single matrix. No, the models need to learn how to deal with permutations. So they need to learn how to complete every matrix in the equivalent class. That is, every matrix that can be obtained from a single Hadamard matrix by introducing row and column permutations and negations. And notice that there are n factorial, where n is the size of the matrix, times n factorial different ways that we can apply different row and column permutations. And there are also 2 to the nth power different row and column negations. So the sizes of just one equivalent class is huge. There are a lot of examples. And however, these symmetries in the data can be exploited. How? So suppose that we want to learn, or that we have already learned to complete some matrix H. And if we introduce a permutation to the rows or columns, the values required for correct reconstruction must not change. The only thing that was affected was their position. The values themselves were not. To illustrate this, we can look at the image below. On the left, we have a matrix with zeroed out entries, and if we apply any permutation to its rows, the values required for correct reconstruction will not change. The only thing that must change is their position in the predictions of the model, right? So, of course, neural networks such as multi-layer perceptrons do not have this inductive bias in their structure. Therefore, if we apply some permutation to the input, the MLP could output something that is completely different. And it will have to learn this relationship between permutations to the input data and permutations to the output data through data augmentation strategies. So our goal is to exploit this behavior towards permutations. And this is formalized as the notion as equivariance to row and column permutations. So formally, if P1 and P2 are any two permutation matrices, and if F is some function, neural network or otherwise, that reconstructs Hadamard matrices, then it should obey the following equation, which basically states that if we have some matrix and we apply permutations to it and then feed it to F, it should be the same as applying F to the original matrix and then applying permutations. And this is often better understood by looking at commutative diagrams. So what this says is that if we want to complete H1 using function F, if we apply permutations to obtain some type of intermediate matrix H2 and then apply F, we should arrive at the same result as applying F to the matrix that we want to reconstruct and then apply the permutations to the predictions. And this is a big part of what geometric deep learning studies. And geometric deep learning focuses on exploiting these symmetries in data and rests mainly on three pillars, which are group theory, notion of invariance, and notion of equivariance. And the notion of equivariance in the previous slides can be extended to arbitrary groups. And please note that fully understanding what a group is not fundamental for the rest of the talk. It just so happens that groups are the ideal mathematical structure to think about transformations being applied to the input. But nevertheless, because it formalizes things a little bit and makes talking about equivariance easier, I'm going to briefly explain what a group is. So basically, a group is a set together with a binary operation that maps two elements of G into another element of G that obeys the following properties. It is associative, meaning that the order in which the operation is applied to a sequence of elements is irrelevant. There is an element denoted E and referred to as the identity, such that for every element G, and G together with E is still G, and every element has an inverse, meaning that. So, and the group action is simply a function obeying this rule that basically states that if we act on X using G2 and then not act on that new element using G1 is the same as acting on X using G1 multiplied with G2. And now we can formalize the notion of equivariance to functions for arbitrary groups. And basically a function is said to be equivariant to some group action if we apply, if F applied to group action of G to X is the same as applying G to F of X. And this is the same as the previous definition here of equivariance to permutations, but generalized to other groups. And this may seem like a lot of unnecessary formalization, but in fact, the intuition behind these concepts has been used for quite some time in fields such as image recognition, using, for example, convolution. So suppose that we have a cat or another object in the leftmost top corner of the input matrix, and then we, of course, the filter applied to that square will yield a certain value in the output matrix. But if we shift that object 1 pixel to the right, the output of the layer will simply have the value in the output shifted accordingly. So convolution is just equivariance to translations. So how do we construct an equivariant layer that acts on square matrices and input and is equivariant to row and column permutations? So a simple way to do that is to apply a function entry-wise to every element in the input matrix. So the layer would be something like this. It would receive a matrix M, and it would apply some function psi to every element in the matrix. Of course, this is not very, we need more than this to have accurate classification, right? Because this is only using local information about each entry. So it's impossible to classify. If we have a 0, it's impossible to decide if it should be -1 or if it should be 1 based on that entry alone. So we need some sort of scheme that gathers information about the whole matrix and is still equivariant. And we do this using a system similar to message passing in graphs that works as following. Basically, to compute the value of some element x, y of j, where j is simply the index in the matrix, we gather information in its column and in its row. So we pair x, I of j with every element in its row, and then we feed those pairs to functions, psi, and we do the same for its column, and then using invariant aggregator to permutations O plus, it's the symbol here, this O plus denotes, and it's the O plus after using. Unfortunately, my Google Slides laser pointing isn't working. So then we aggregate all these results from these pairs after the function psi being applied in an invariant way, and that will be the entry in the output matrix. And an invariant operator is simply an operator that remains unchanged after applying some permutation to the data. For example, summing over a list of elements is invariant with respect to permutations, because it is, of course, invariant regardless of the order of the elements. Also, multiplying every element in the list is invariant as well, such as the average or the maximum elements. Those are all invariant operations with respect to permutations. So our layer in the model works something like this. So we are computing the first entry. Now we are computing the second, and we pair it with every element in its row and in its column, and we feed it to functions psi. Then we use O plus to merge the results of every psi, and that will constitute the respective entry in the output matrix. And why is this equivariant permutations? Well, if, for example, we simply switch the first and the second column, the information that the layer will have to compute the value will be exactly the same. It will simply have been shifted forward. So if we apply a permutation here and then apply the layer, it will be the same as applying a layer and then applying a permutation, the same permutation. So exactly, this is how our layer works. We have an element, we pair that element with everything in its row and its column, feeding those pairs to functions psi, and then we aggregate everything with an invariant operator that will correspond to the next entry. In our particular case, functions of psi were simple, dense layers. So the full model simply receives a matrix as input, then it applies several layers of message passing, and then a final classifier. And this final classifier is simply that first layer, which I explained, that applies some function to every entry in the matrix, but because now we are using it, the end of our model, it already has collected information about the entire matrix. And why has it collected information about the entire information when we are only using information in its rows and columns of every element? So, for example, look at the first entry in the second matrix. By that I mean the matrix that results after applying an equivariant message passing layer to the input matrix. We can see that it has only gathered information about its row and its column, meaning that it has no information about element D. However, now in its row and in its column, we already have information about D. We have psi of CD in its row, and we have in its column, and in its row we have psi of BD. So if we apply another message passing, so if we do another message passing round, we will have collected information about the entire matrix. So how do we generate data? First, we start with a representative of the equivalence class, and this is just for the scenario where we are training and validating the same equivalence class. And then we permute rows and columns for models that are not equivariant to permutations. And this is simply a data augmentation strategy. And then we negate rows and we negate columns, and we do this for all models. And this is simply another data augmentation strategy because at the moment we are not exploiting symmetries related with negations. Then we choose the number of entries to zero out, and then we randomly set that number of entries to 0, and we start the missing value. So our data set consists basically of tuples, where we have a matrix with some zeroed out entries, and the training data will simply be the values that must be completed with their respective position. So what we did first was we compared our model to baselines, and we tested our model against neural networks such as convolutional neural networks, multi-layer perceptrons, and few tests on transformer-like architectures. From all these baselines, the convolutional neural networks yielded the best results, and we measured their performance. And we measure their performance using what we call a one-shot matrix reconstruction, where basically we complete the matrix using our model by simply summing the input matrix with the sign of the prediction. So recall that the elements in the training data are matrices, and their predictions are values between -1 and 1. So a negative value here would be decoded to -1 and a positive value to 1. And this scheme we call message passing value. And in the next table, we see the results of convolutional neural networks, which from all the other baselines yielded the best results against our model as a function of the number of zero-dot entries for sizes 8 and 12. And we can see that using message passing, we vastly outperformed convolution. And regardless of the size and the number of entries, our model performs better. And I'd like to emphasize that when moving from size 8 to size 12, we've tried to double the size of the filters, try to double the number of filters in each layer, and tried those two together, and there were no significant improvements to the performance of the convolutional neural networks, whereas our model was trained with the exact same architecture from sizes 8 through to sizes 32. And the same amount of data as well. Then we tested against the recovery algorithm presented in Klein's paper, which we referred before. It was the paper that found matrices of size 228 and the symmetric matrix of size 116. And the recovery algorithm always recovers with probability 1 asymptotically and squared over log n entries. And for sizes 12, 16, and 20, our method outperformed Klein's recovery scheme. However, we were soon outperformed by Klein's when increasing the size and the size of the matrices. And again, I'd like to emphasize that our models maintained the same architecture throughout the experiments, and they've also seen in each epoch the exact same number of matrices. And nevertheless, increasing the size of the matrices doesn't completely break the learning procedure. Instead, we can see that always the model is learning something. And this was, we didn't do any fine tuning for sizes 32 to try to make it outperform Klein's method. And looking at the graphs, interestingly enough, for large sizes, we can see that both methods go to 0 at exactly the same number of zero-dot entries. And we'd like to stress that our model was not trained to replicate with data from Klein's method. It wasn't trained to replicate this method. It was trained by simply looking at matrices and their completions. And in training, we also included matrices with more zero-dot entries than what was predicted by Klein's method asymptotically. And even though our method was not trained using Klein's, and even though our method saw matrices with more zero-dot entries than what Klein's method is able to decode, they, for some reason, go to 0 at pretty much exactly the same point for all sizes above a certain order. So now, a little bit about data generation for several equivalent classes, and the data procedure is pretty much the same, except right before training, we separate a few representatives of equivalent classes for generating the training data, and we separate other representatives for validation data. And then the data generation follows the exact same procedure as it was previously explained. So the plot on the left we've seen before, it's the same plot of the graph using the graph we've seen here for size 28. And I'd like also, I think I might have overlooked this because I've looked at these graphs for some time, but I think I need to explain better what they are. So basically in the y-axis, we have the percentage of successful reconstructions, and in the x-axis, we have the number of zero-dot entries. So these plots are measuring the performance of the reconstruction of the models as a function of the number of zero-dot entries. So here we have the plot that we've seen before, which is the reconstruction capabilities of our model as a function of the number of zeroed out entries for a single equivalence class. And on the right, we have the plot illustrating the same construction capabilities, but for a model that was trained on just 24 of the 487 equivalent classes. This corresponds to just 5%. For size is 28. So we separated 24 equivalent classes. The remaining ones were used for validation. We trained the model on just those equivalent classes, and then we try to reconstruct matrices of unseen equivalent classes, and we obtained the same performance as, you know, reconstructing in training and reconstructing the same equivalent class, which, you know, it's a very good result with regards to the generalization capabilities of our models. We also looked at other metrics after training the models. One which I would like to highlight here is the highest confidence prediction metric, which basically works like this. We make a prediction using our model. We choose the one with the largest absolute value, and then we test if it would correspond or not to a correct decoding. And on the right, we have a plot that illustrates this highest confidence prediction as a function of the number of zeroed out entries. So for size 32 and for all the other sizes, I'd simply we simply have here only size 32 to unclutter the plot. We can see that the accuracy is always above 96%. So regardless of the number of entries, the model's most highest confidence prediction is pretty much always right. So out of curiosity, we try to use our model to reconstruct matrices as a sequential procedure, which works as follows. We make a prediction, then we complete just the entry with the highest absolute value, and then use that matrix to make a new prediction. So something like this: we have a matrix with zeroed out entries, we make a prediction, we select the highest absolute value, and we decode in the original matrix to the sign of that entry until we've arrived at a matrix with all entries reconstructed. And using this sequential reconstruction, we can outperform Klein's method. So here we see the percentage of successful sequential reconstructions of our model as a function of the number of zeroed out entries, and we can see that its performance vastly improved, and now you can reconstruct matrices well above Klein's bound. Okay, so what have we seen? We have seen that machine learning can in fact be used to reconstruct Hadamard matrices, which, you know, leaves us a little bit hopeful that we can use these models in future works where we can try to use reinforcement learning to simply maximize the determinant of matrices, or we can use these models in branch and bound policies to improve variable selection. And we've also seen that success in the reconstruction task seems to be heavily dependent on exploiting domain symmetries, and that using one-shot reconstruction we came short of theoretical baselines, but as we've seen, with a simple sequential procedure we can outperform theoretical baselines, which seems to leave room for improvement using, for example, search methods. So I think this concludes my presentations, and if anyone has any questions, I'll be happy to answer them.
Yes, we have now some minutes for questions. You can either ask them using your microphone, or you can also ask them in the chat, and I or Augusto will read them. So Professor Mario Figueiredo.
Yes, I have a question. Hello. Nice talk. Thank you very much. So, can you show the slide where you define the definition of success, and you have the first plots.
Yes. This is the one.
The one before that.
Here.
Yeah. So by you just how do you count a successful reconstruction? It has to be a precisely Hadamard matrix.
Yes, we are not counting successful reconstructions as the model predicting an accurate mask in the data set. We are actually really testing if the reconstructed model is a Hadamard matrix, which can be done fairly quickly. We simply multiply the matrix by its transpose and see if it's a diagonal matrix. And the way we are obtaining these values is for each number of zeroed out entries, we generate 1,000 matrices, and then we ask the model to make 1,000 reconstructions, and we count the ones that were successful, and we divide by 1,000. So we obtain this percentage.
So you don't measure, you don't even think about measuring how far away the reconstruction is from being a Hadamard matrix.
No, we are
because
not
it can be
measuring
really
how
close,
far away.
right? And you're counting it as a failure.
Yeah,
But there are different levels of failure, I guess.
Exactly. It is in this case, it is either a failure or a success.
Okay, the other question I had was about this, still in this slide. So do you have any intuition why the convolutional network worked better than the multi-layer perceptron? Because there seems to be there's no shift equivariance inside the matrix, right?
No, there's no shift equivariance inside the matrix, and we are not quite sure why convolutional neural networks outperform multi-layered perceptrons. We ran several experiments with networks of different sizes, different batch sizes, different epochs, and it just so happened that convolutional neural networks for sizes 8, 12, and 4 was not as it seems that it's more robust with regards to permutations of the input matrices.
Could it be that it's because they have much fewer parameters?
Not sure. I think I'd have to look a little bit deeper into why they are more robust.
Thank you. Yeah, thanks. Very nice.
Let's see if we have more questions. Well, I have a few, so maybe I can ask one while people are still thinking of their questions or writing them. So I know that a few conjectures in math have very deep consequences. For instance, the Riemann hypothesis has a lot of implications if it's true. Is it the same for this Hadamard conjecture, or it's just a problem on itself and there aren't many results that depend on it being true or false?
So yes and no. I'm not sure if there are many results that were proved by assume that the Hadamard conjecture is false, or assume that the Hadamard conjecture is true. So disproving or proving would have serious implications in theoretical mathematics. But Hadamard matrices by themselves are objects that are used often. For example, in error correcting codes, they were actually used to reconstruct images that arrive from the surface of Mars. So the matrices themselves have applications in several fields, such as error correcting and even quantum computations, but the conjecture itself, I'm not well aware of the practical implications of proving it and disproving it, other than it's a difficult problem, and on itself the result would be very, very, very interesting.
Okay, thank you. Two people have raised their hands, so I don't know who was first. So maybe you, Ines, can ask now your question.
Yeah. Hi, Augusto. Thanks for your talk. I don't think I understood the relation between these reconstructions models and the conjecture. Like, do you plan to use these models to try to prove or disprove the conjecture? And if so, how will you do it?
Okay, so not directly. It's hard to think of a way in which we could use the models to prove or disprove the conjecture. It would revolve around finding a counterexample. For example, people have done that for graphs. There is a recent paper where they use reinforcement learning to construct counterexamples to small conjectures over graphs. The way we plan to use these models is, for example, in reinforcement learning scheme where we reward the agent as a function of the determinant, and hopefully we have an agent that can start from a random matrix and maximize its determinant, which will have an optimal solution by finding a Hadamard matrix. We are also working on expanding this work of reconstruction using reinforcement learning to successively reconstruct matrices with more and more hidden entries, which maybe will allow us to, in the future, ask a model to simply generate Hadamard matrix given a few rows. And another thing that we plan on doing is that there are no constraints on the size of the input matrix in our model. For example, if we are using a multi-layered perceptron, we need to have a multi-layered perceptron for matrices of size 4 and a different one for matrices of size 8. Here we don't have that restriction on size, so it might be possible, and in fact this already happens often in reinforcement learning over graphs, that we train on small examples and then our models can generalize well to instances of much larger magnitude, which will allow us to hopefully, because we are still working on this, train on matrices of size, for example, 32, which is the last size for which all equivalence classes are known, and then discover matrices that, even though they don't prove or disprove the conjecture, are still unknown. Because, as I said before, even though we know all matrices, we know at least one representative of all matrices up to size 668. 32 is the last order for which all matrices are known. Of course, this is speculation, and we have work progressing in this line of research, but at the moment we don't have strong results to show here.
Thank you.
We have at least one more question by Luis Espírito Santo. Luis, please, can you?
Yes. Can you hear me?
Yes.
Hi, Augusto. Thank you very much for this talk. Great work. I have one quick question and two rather bigger questions. The first one is, how did you implement this? Which kind of framework did you use? Did you try to parallelize it? Just out of curiosity. Yeah, okay. You can answer that.
So we implemented everything in TensorFlow. To go a little bit deeper, we implemented that layer by inheritance from other layers, as people usually do in this type of tasks. And then our models are simply sequential models where the layers are our own layers and the final layer is an entry-wise classifier. And no, we did not parallelize this. We ran a few smaller experiments on our local machines, and then for larger sizes, we ran them on the cloud using machines with larger memories.
Yeah, so regarding that, I was thinking how I would implement this, and one question, well, this raised one question, that is, how is this different than a convolution, like a cross convolution? Do you understand what I mean? Is like, instead of having a block or a patch that you pose on top of the image, you have like cross patterns that you apply. Or was that the way? So you enriched it from the convolutional layer to implement this, or did you use something else?
We use something else, but the way we've done this is probably by no means the most efficient way of doing it. What we do in TensorFlow is we receive a matrix as input, and then use a few TensorFlow default functions such as gather and stuff like that to build matrices that contain these pairs that we are seeing here. And then we apply our size, which in our case are dense layers, to those matrices with pairs. And then finally we sum. By the way, the invariant aggregator that we used was summation over the pairs to obtain again a matrix of the same shape as the input matrix. I don't know if these answers are your question.
Yeah. Well, yeah, it answers my question. I was just thinking if we could implement this by leveraging our notion of convolution, but instead of using the patches like squared or rectangular patches, using like a cross-shaped pattern.
Yeah,
maybe.
Yes, probably there is a way of doing that. And in fact, equivariance is deeply related with convolution in its purest form.
And my last question is, you said that you didn't use any kind of architectural trick to put bias, like the negation bias on the columns. Yeah. So did you give a little thought on how would you do it, and can you share it with us?
So at the moment, we don't have any strong results in how to put bias with regards to negations, but we are working on that. And I actually have a meeting sometime this week to do a little bit of brainstorming. But at the moment, we are still unsure how we would implement both inductive biases at the same time.
Okay, thank you. Great.
Okay, let's see if there are more questions. I have at least one more, and I'm curious about it. So I will ask, and if someone else has a final question, just please ask it. So my question is, if you have any intuition, I have one, but I want to hear about yours, on why the sequential approach apparently at least works much better than deciding all the entries in a single step.
Yes, we believe that we believe that asking a model to make a single correct prediction at a time is easier than asking the model to make 50 correct predictions in a single row. And then if that prediction, the highest confidence prediction, is correct in theory, the next reconstruction, because it has one less entry to complete, should be easier for the model. So I think that mainly it leverages on that, in the fact that it is likely that the model, it is very unlikely that the model has failed for every entry in the matrix, and probably the one with the largest absolute value is the one that is in fact correct. And after completing that, now the task is a little bit easier, and again the model is very unlikely to fail everywhere, and probably the entry of the prediction in highest value is again correct, and it goes on like that. However, interestingly enough, the successful reconstructions does not correspond to, and we tested this. So here we have the highest confidence prediction of the model, and it's always above 90%. Yet for example, 50 entries, the percentage of successful reconstructions is below 96 to the power of 50. So the model, so this is not the same as doing independent Bernoulli trials with always 96% accuracy.
Couldn't it be as well because if you predict one by one, then you give some chance to the model of correcting errors, like in the sense that you might miss one entry, but you can compensate with changing another, and at the end, your matrix will still be a Hadamard?
Oh, no. In fact, the model's performance is below what would be expected if it were independent by Bernoulli trials. So if we had to guess why, and disclaimer, we didn't look very, very deeply into this because we are still studying the model and trying to understand how they work, is that when we introduce a lot of errors, we have in the matrices a few blocks of rows and columns that are very, very, very corrupted. For example, something like half the column is missing, and this will happen because of the pigeonhole principle. If I put 70 missing entries in the matrix with only 32 rows, of course, that at least one will have a lot of corrupted entries. And this isn't likely to happen when we are, only introducing 10 missing entries. So probably what happens is the model starts by reconstructing entries that are more or less alone, and then it reaches a point where it's only seeing entries that are very, very, very corrupted, which corresponds to data that it doesn't see often during training. So that's why that's one of the reasons we believe that the performance is below what would be expected.
Okay, thank you very much, Augusto. Very nice talk once again. I think there are no more questions. So yeah, that's it. Thank you again to you and Inductiva for accepting our invitation. It was a very nice talk and a pleasure for us to have you here. And we look forward to the next machine learning seminar in 2 weeks. So I hope to see you all here. Thank you very much for your presence.
Thank you for having me.